In this lesson, we'll be taking a look at the volume of cylinders. Before we actually do that and get into our feature question of is a cylinder actually a prism, let's take a look at what prisms are, since it's something that's probably new to your experience. In the last video that I recorded, we looked at prisms, and to be a prism, these are the ingredients that are necessary. It has to be a three-dimensional solid with parallel bases, and each parallel cross-section must be congruent to the base. So let's take a closer peek at this prism here and take a look to see what makes it tick. So this is a prism because it has parallel bases. So it's got a surface that is parallel to another surface. And if we slice into this object or this solid anywhere along the height, we'll end up getting exactly the same or a congruent shape as the base of the shape. So you could think of, and you should think of a prism as a stack of congruent shapes laid out on top of each other. I think a nice way to think of it is like a loaf of bread, and here the baker goofed, and the loaf of bread is this weird triangular wedge, which is mathematically called a prism. The same thing goes for something like this. Let's call the bottom and the top our bases. These parallel bases are connected by a height, and anywhere we slice into this rectangular solid, we'll end up getting the same rectangular solid surface as our bases. So those cross sections are identical to each other, and since that's the case, it's considered to be a prism. And the same applies for this one here. Here the bases are pentagons. The height connects the bases together. Remember, sometimes the height is not up and down. Sometimes it's side to side or diagonally. So a height doesn't necessarily mean the height going up from the bottom, because sometimes the bottom is, right in front of us, as it is here, not on the bottom of the table, wherever this object is sitting. So anytime we slice into this prism, as long as we're slicing parallel to one of the bases, we'll end up getting an identical base, or an identical slice, or an identical cross section. So let's see, how about a stack of library books? Do these fit the description to be a prism? All right, do they have parallel bases? Looks to be parallel, a stack of books. This one has a stack of books where the top and the bottom are parallel to each other. This is going horizontally, the bottom's going horizontally. We've got a bunch of horizontal surfaces there. Each cross section, each book is exactly the same. So this would definitely be an example of a prism. And this might be better if it was small sheets of paper, but this does approximate, that's what we would say it mathematically, approximate a prism. And since that's true, we can actually figure out the volume of these shapes by using big B times H. As a good exercise for you, why don't you try to figure out the volume of these three prisms? The triangular prism, the stack of books that's going exactly straight up, and also the slanted stack of books. Figure out the volume for those three. All right, so how'd you do? 9,000 for the first one, and both stacks of books on the bottom have exactly the same volume, which does make sense because these books are taking up the same amount of space, even though the second stack of books has been slanted somewhat. It's still the same amount of material to make those books, so the volume is exactly the same. And that is something that is called Cavalieri's principle, that it doesn't matter if the prism is directly perpendicular to the base or if it is at a slant height. And we've seen an example like that in the last video. All right, so on to our central question for today. Are cylinders prisms? Well, cylinders are also referred to as cans. They're called canisters, pipes. Those are all examples of something that's called a cylinder. But so are cylinders prisms? Do they have parallel bases? Are the bases congruent to each other? And when you slice into a cylinder, do you get exactly the same cross section? Well, I'd say yes, right? If we actually sliced into this canister, anywhere we sliced into it, as long as we're slicing parallel to the bases, we end up getting exactly the same cross section as the bases. So yeah, so cylinders are prisms, and if since that's true, we can use volume equals big B times H to figure out their volume. So why don't you try that as an exercise? Figure out the volume of these two cylinders using volume equals big B times H. Then unpause the video when you're ready. All right, so using volume equals big B times H to figure out the volume of this prism, you could see that big B is the area of the base, and since the base is a circle, I'll be replacing capital B with pi r squared. The radius of this cylinder is 8, so I call the radius 8, and the height that connects both the bases together is 6. So altogether I'm getting pi times 64 times 6, which is pi times 384, or 384 pi. The second example is practically identical to the first, except I had to notice that they gave me the diameter. So in big B times H, when I replace big B with pi r squared, the radius would have to be not 4, but 2 from the center of that circle to the circle itself. So we get pi times 2 squared times 3, which is the height. So 4 times 3 is 12, so 12 pi, or pi 12 is the answer there. And then for convenience, sometimes this is written, instead of writing it as big B times H, sometimes it's helpful to see it in a different way. And some books actually refer to it, and the New York State at least currently refers to it as pi r squared times H, which I disagree with. I think they should just call it the convenience of calling it volume equals capital B times H is to hammer the idea home that no matter what the shape is, as long as the shape is extending itself up and down the height, it should be following the same formula. So there are 2 more questions here at the bottom. I'm not sure exactly if you've seen those yet, if you don't have the worksheet. And we'll be working through these 2 examples. So you can pause the video and then resume when you're ready. So on this one here, we have to figure out the volume of the pipe, which is following my plan here. I treated the entire pipe like it was actually rock solid all the way through, full of concrete, and figured out the volume of it if it was solid, and then subtracted away the hole, which represents another cylinder, an empty cylinder. So basically there are 2 cylinders here, the outer shell and then the inner hole of the pipe. It's called a culvert here, which I imagine they probably use that in like drainage or sewage. So it's pi r squared times H to figure out the volume. It says that the diameter of the overall pipe is 1 meter, so that the radius would be half of a meter for the radius. So a half squared is 0.25 times 4 is 1. So 1 times pi would be the volume of the pipe if it were solid. As for the hole has a diameter of 0.8, which means the radius is 0.4. So I use pi r squared times H again, replace the radius with 0.4. The height connects the bases together. The height is 4. So 0.64 would be the volume of the hole, and then subtract the whole entire object from the hole, or take the hole out of the object, subtracting the 2 gives you 0.36 times pi. In this last example, they're not giving you a picture, so I would recommend drawing a picture for it. Draw a picture of a hockey puck and answer the question, what would the volume be for a package that would hold 6 pucks stacked up on each other? So here's my picture of the hockey puck. And I figured out the volume of a single puck and then multiplied it by 6 to figure out the volume of a cylindrical package that would contain all 6 pucks. So picture a whole canister of pucks together if there were 6 pucks. Figuring out the volume of one particular puck and then multiplying that by 6. I think that brings us to the end of the lesson. Yes. So what's left for you to do is to try these questions that remain, and it looks to be like a nice, decent mix of questions that have pictures and questions that don't. In fact, I guess there's more than a couple questions that don't have pictures. So it makes it a little bit more of a challenge for you. This one does not even have any cylinders, but just some prisms stacked there to figure out the volume. Well, the question doesn't say what to do, but obviously it's to figure out the volume of that object. And as a final challenge question here, a question that was on the Regents exam a few years ago is involving the swimming pool here, which will involve using some volume and some other tricks that you learn throughout the year. And hopefully you challenge yourself to give that a try and see how far it can take you. Watch your rounding on this question in particular, because that's a place where you could easily get yourself sunk. No pun intended. Have a good day.